this is gonna be fun.
Not at the moment. We're trying to get these data into the Weather Service office in Indianapolis so that they can use them to help issue warnings, because actually we're between their two radars. The two closest ones are in Indianapolis and Chicago. So because of the curvature of the Earth, by the time the radar beams get here, they cross almost a mile above our heads. So we're trying to fill the lower atmospheric observing gap. So this would be like if you were up in space looking down at the Earth and you could see the pattern of precipitation around here. So we're at the center of the bullseye here. So 50 kilometers, roughly 36 miles or so. So not 50 kilometers.
Oh,
yeah,
right.
not super long range, but radars, Weather Service's radars by comparison can see out to 230 kilometers. This guy can see out to 50.
So we're right in that bullseye?
We're right in the bullseye. The wavelength is about 3 centimeters, so each wave that goes out is about 3 centimeters long. The ones the Weather Service uses are 10 centimeters, which is better for detecting hail. So that's why they use that wavelength. This one. So this blob here, this represents, the colors represent the intensity of precipitation. So if you were to drive a car through this, you'd be going through really heavy rain here, and then it would stop when you got back out into the gray area. Your beam, radar gun, pointing out at the atmosphere. Now I need you to spin around 360 degrees all the way. So that's when you get back to where you started. Then raise your arm a little bit and spin around again. So you get back to where you started. Raise it up a little more. Spin around again. And then basically you keep doing that 10 times and then come back down to where you started from. And that is the scanning pattern that it does. It also does one vertical scan where the dish actually rolls onto its back and points straight up. And that's for calibration. Meaning we want to make sure that all the numbers on there mean the same thing. Buildings and trees, and that's what these echoes in here close to the radar are called. That's called ground clutter. That's not something we want. This is something that we can fix with computer programs. We can get it to scrub those out. But when it comes back around this sector, you'll see. So this is the top part of the storm. Now we're back to the bottom part. So now we can see that it's moved a little bit.
Wait, is it scanning us right now, or?
It's not scanning us because we're beneath the radar. The radar beam is going out. It's aimed at the horizon and up, so it never scans people. Yeah. So there's a few sectors that are blocked by like the clock tower, the water tower. Those are kind of thorns in my side, but we find ways to deal with them. We put a mask on the data when we analyze it and say, okay, these particular azimuths, these particular angles are suspect. All right, you guys ready to go up?
All right.
All right. So just to explain what you're looking at there, you see there's a large dish rotating around and around. What that dish is doing is focusing the signal so that it gets concentrated into just a nice flashlight beam and goes out into the atmosphere. when it comes back, it catches all of the reflected energy. And so it's kind of like when you cup your ears or your hands behind your ears in order to hear a very quiet sound. The dish acts like that. So it's like a big Mickey Mouse ear listening. Okay, so that is a great question. So the dome is made out of a substance called fiberglass. So that's kind of like a mixture of like plastic and fiber.
Okay.
And what that does is it's invisible to the radar.
Oh.
So the radar can actually see through that even though we can't see through it with our eyes. It's just shooting its energy out through that dome as though the dome wasn't there. The dish itself is 2 meters, so we wanted to make sure that that would fit in and actually, be able to rotate all the way around and have plenty of clear.
This is actually pretty cool.
You like that? The big is the whole dome, so I think it's about 4 meters across. And then, it has to be big enough to fit the radar in it and allow it to spin all the way around without bumping into the sides. So we want to give it plenty of space. And we also want there to be enough space so that if a technician has to go up there, they can get in next to it and work on it. And a couple times a year, I have somebody fly out from Colorado to work on it. Oh, here's where the radar is going to roll onto its back and point straight up.
I'm kind of scared.
Yeah, so it's looking straight up into the air, and that's that calibration scan again. So the dish is now pointing straight up into the sky. So whenever there's radars that are running 24 hours a day, 365 days a year, and there are meteorologists watching the scope all the time. Anytime, even when you're asleep, there's people at the Weather Service watching the scope, and so if there's ever a severe thunderstorm or a tornado, they're watching it for you and issuing warnings. It goes out to TV, it goes out on the radio, it goes to your phone, it goes to your apps, if you got some configured for that, to your weather radio. Cheapest life insurance policy you can buy. You can program it with your zip code so it's not going off for stuff that doesn't interest you. So I strongly recommend everybody invest in one of those.
But it was really cool to see how the radar worked. We watched it go up. We watched it
I was
spin.
too scared because I thought it was.
Hi, I'm Ezra speaking. Thank you for watching my video. Please like, share, and subscribe, and have a great day.